This is Bill Farmer again. Welcome back to McMaster University course, Computing and Software 701, Logic and Discrete Mathematics. We're talking about first order logic now, and today we're going to talk about axiomatic theories. So an axiomatic theory is one of the most important notions in logic. So we're going to define a first order axiomatic theory, which we're probably from now on we'll just call a theory for short. It's a pair of a language and a set of formulas. The language is a first order language, and the set of formulas are closed, and we call these formulas axioms. So it's a language and a set of axioms. And then an interpretation is a model of our theory if that interpretation is a model of the axioms. And a formula is valid in a theory if that formula is a logical consequence of the axioms. And a theory is satisfiable if the axioms are satisfiable. Now, it turns out I forgot the definition of a set of formulas being satisfiable, so I added that to the slides. It's right here. But it's what you would expect. A set of formulas is satisfiable if there is some interpretation and some assignment such that that assignment satisfies the formulas in the set in the interpretation. Okay, so we know now what a first order axiomatic theory is. We know what its models are. We know what it means for formulas to be valid in the theory. We know what it means for the theory to be satisfiable. Now, the really important thing about theories, which I have written and read here, is that a theory can be viewed as a specification of its models. And there's many examples of theories. We're going to look at some of them, but there's theories of orders, lattices, Boolean algebras. For instance, a theory of weak partial orders, all its models would be essentially partial orders. Weak partial orders. And remember, a model is a structure plus a mapping of the symbols in the language to that structure. Well, anyway, to continue, we can have theories of monoids, groups and rings, fields. These are algebraic theories of algebraic structures. Another important theory is Pressburg arithmetic. This is the theory of a natural number arithmetic with 0, successor, and plus, but not times. We have first order Peano arithmetic. This is a theory of arithmetic with 0, successor, plus, and times. The theory of real closed fields. This is basically the theory of the algebra of the real numbers. And we're going to take example, very specific example, the theory of monoids. So this theory has a language. Right here it is. And we have one constant symbol, E, one function symbol, mul, which is binary, and one predicate symbol, equals, which is also binary. And it has these axioms. Now, we also implicitly have the axioms for equality being a congruence, or representing a congruence relation. Equality is not actually a relation. It's a predicate, but every predicate represents a relation, so it represents the congruence relation. So we haven't put down those axioms. They're implicit. Okay, so what do the axioms of use say? They say first that mul is associative. They say that E is a right identity, and they say E is a left identity. this theory we can call the first order theory of monoids. Any of its models will be monoids. Every monoid will have some kind of binary operation according to Moll that's associative. It will have an identity element according to associated with E. So this is a theory of monoids. Let's look at another theory of strict partial orders. We have no constant symbols, no function symbols, and we have equality and less than. And again, equality is going to represent a congruence. And these are the axioms for less than. Remember, this is strict partial order, so we have irreflexivity, we have asymmetry, and transitivity. And all the models of this theory are going to be strict partial orders. So the interesting thing about these theories, for instance, if we go back to this theory, we know that a logical consequence of these axioms is that there's no other identity element. In other words, E is unique. There's only one identity element. And because that is a logical consequence of these axioms, we know that E is unique. The identity element is unique in every monoid. Every monoid that has ever been written down, ever thought of, even monoids that no one has thought about yet. Okay, so now let's look at a little more sophisticated situation, Peano arithmetic. So, a famous Italian mathematician and logician, Giuseppe Peano, in 1889, he came up with a set of axioms to capture what Peano arithmetic, what natural number arithmetic is, which we now call Peano arithmetic. And so basically he came up with a language, which was not a language of first order logic, but of second order logic. And he had a constant 0, a unary function symbol S, and a binary predicate symbol, which stands for equality. And 0 represents the number 0. S represents a successor function. That's the function which we can represent with a lambda expression like this. And then U has the following set of axioms. It has axioms that say that 0 is not the successor of anything. The successor function is injective, and we have the induction principle, and this corresponds to the normal weak induction principle, or what people often call mathematical induction. And these two axioms basically are no confusion axioms. So basically he's defining the natural numbers as an inductive set. So this is no confusion. And this is no junk. No confusion means that we can't get to we can't get to the same natural number using successor in different ways. And no junk means there are no other natural numbers except the natural numbers that we can get to from that are either 0 or we get to by applying successor a number of times. Now in this theory, we can define plus and times. We need to use the induction principle to do that. And this theory is categorical. That means if we're talking about it with the normal kind of semantics, there's only one model up to isomorphism. And that one model, if you look at the domain, it's going to have things corresponding to the natural numbers. Okay, now the one thing to notice is that we had to use second order logic to express this, because here, let me use a different color. Here, we are quantifying over unary predicates. In first-order logic, we can't quantify over predicates, so we can't express this in first-order logic. We can only express it in second-order logic or something higher like simple type theory. Okay, but there is a way of approximating this logic in first-order logic. And this is what's called first-order Peano arithmetic. Often it's just called Peano arithmetic. So here, our language is a little bit different. We have zero, successor. We do have plus and times and equality. Notice that we don't need plus and times as primitive functions in normal second-order Peano arithmetic because we can actually define them. Here, we need them. We need them as primitives. And then we have the following axioms. These are the no confusion axioms. And these are the recursive axioms for plus, the recursive axioms for times. And then we have this thing which is called the induction schema. Now, the reason it's called an induction schema is it's a schema in the sense I can plug in for B any formula of my language. I can plug in my formula, and these formulas represent predicates. So if remember, with the induction principle, this is something that's true for all predicates, unary predicates. Here, we're going to represent predicates with formulas. Now, there's a problem in doing this. The problem is that if we go back up here, how many predicates are there on the natural numbers? Well, the number is uncountable. And if we go back here, how many formulas are there? Well, the number of formulas is countable. So there's an uncountable number of predicates, and we can represent a countable number. So we're missing many instances of the induction principle. So this theory is only an approximation of Peano arithmetic. And because it's only an approximation, it is not categorical. It's a non-categorical approximation, which means there are many models of this. And there's one model, which we call the standard model. That's a model where we have as our values 0, 1, 2, 3, and 4. But there's also non-standard models. And these models have infinite natural numbers, natural numbers that are bigger than all the standard natural numbers. And these kind of natural numbers, they always have a predecessor. So you can keep finding, there's always a predecessor. You never get down to zero. You only get down to zero by taking the predecessor when you're talking about the standard natural numbers. So this is a little strange. This is a little bit disconcerting, really. But this is a result of using first-order logic, trying to force second-order Peano arithmetic into first-order logic. Okay, so I want to talk a little bit about theories versus models. So we can think of a structure as a concrete mathematical model. It's like the simplest kind of mathematical model. Remember I said mathematical models are built from structures. So the simplest mathematical model is a structure. But we can think of a theory as an abstract mathematical model. It's not concrete like a structure. So a structure, we have actual values, and we have actual functions and predicates. With a theory, we just have symbols that denote some kind of unspecified constants, unspecified functions, and so forth. So as I said before, you can think of a theory as a specification of its models. So a theory is both a model itself, an abstract model, and a specification of a set of concrete models. And it's useful to think of a theory is to a model as a specification is to an implementation. So if we're talking about software, a theory is to a model as a software specification is to a software implementation. And so when people write down software specifications, they are very much like theories. And in some systems, they are theories. Now, I want to say one more thing about axiomatic theories. They fall in two categories. Those that are intended to describe a single model. This is like natural number arithmetic, or like if we're going to describe the real numbers. And then there are theories that are intended to describe a collection of models. These are the kind of theories which are specifications. So, for instance, the theory of monoids. Okay, so we're going to stop here. Next time, we're going to talk about truth versus proof.